Still considering sinusoidal functions. Now, previously we looked at transformations of sinusoidal functions that deal with the amplitude. And now we're going to take up horizontal dilations. And so let's look first at this basic function equation, where we got y equals a times the cosine of bx plus c, which is in parentheses, you see, plus d. Now, this a here, coefficient in front of the sinusoidal function, affects the amplitude, and we looked at that. How far is it from the high point to the midline, or from the midline to the minimum point, maximum, minimum, midline, so on and so forth. The B here affects the period. And that's what we're going to focus on. But while we've got this equation in front of us, C is going to affect what we call a phase shift, and D is a vertical dilation. So, and we'll deal with those later. But right now we're talking about the period. Now, you see here that I have graphed f of x equals the cosine of x. And let's think, so if in respect to the origin, I see here that the cosine, let's say, begins at 1 and then it comes down. And by the way, this scale is actually in pi over 2 at this point right here. This is pi over 2. Think about the unit circle. Down here is pi. You see pi right there. This point right here would represent 3 pi over 2. And back up here, we're at 2 pi. And out here on the outer edge, right out here, actually is 4 pi. And so this represents 2 periods of this cosine function. Now, the way I might measure the period is I'm going from, okay, well, how far from this maximum to this maximum, from here to here, have we traveled along the x-axis? And of course, we also know that one trip around the circle is 2 pi. If we start at 0 and we go all the way around, we got to 2 pi. And so in this parent function here, our period is 2 pi. We start right here at 0 and we reach this same point. We're repeating this same point, and that describes our period. Now let's look at a transformation of this cosine function. Now there in the, looks like green, in the green, that is this function here, just f of x equals the cosine of x. And then we have a transformation where we got g of x equals the cosine of x over 2, or that's actually what? The same as saying 1/2 times x. Now, algebraically, here's how we determine the period. We take 2 pi and we divide it by the absolute value of b right here. And in this case, b is 1/2. So we got 2 pi over the absolute value of 1/2. And of course, the absolute value of 1/2 is just 1/2. And so then we got 2 pi divided by 1/2, or it is the same as 2 pi times 2. And you could say 2 over 1 if that helps see that. In other words, if I'm dividing by a rational a fraction, that's the same as multiplying by its reciprocal. And so our period, our dilation is 4 pi. And we're going to see it takes 4 pi to complete one period, or one cycle, if you will. And if I look at the red, well, I see that I start here at 1 when x is at 0. Again, visualize that unit circle. We're over here on the right end of the x-axis, and we're circling around. And of course, right here is pi over 2. And right down here, we're at pi. And up at this point, we're at 3 pi over 2. And here we're at 2 pi. But we have not yet, in this red, completed a circle. See, we're going from here and we're down to here. Well, right here is 3 pi, and right here on the outer edge, the right edge, that's 4 pi. And that matches what we saw algebraically. To go from here, we travel down, we cross the x-axis at pi, we cross the x-axis again at 3 pi going up, and we finally make the end of this period at 4 pi. Well, Shazam. Okay, well, let's see. Let's take a look at a sinusoidal function. Let's also, before we leave, let's think about the characteristics of just a cosine function. In respect to the origin, we see that it starts up here at 1, unless we've got an amplitude change, which would be affected by that A. And we travel down, we're headed downward, we're decreasing until we reach to pi, then we begin to increase up to 2 pi, and that, of course, describes our period. We're next going to look at a sine function. So I've got both of these already graphed, but once again, the same thing holds true. The A affects the amplitude, the B affects the period, C gives us a phase shift, and D gives us a vertical, actually changes our midline is what we're going to discover. Now in the green on this graph, we see f of x equals sine of x. And so again, now with respect to the origin, we're starting right here at the origin. And again, we go up to pi over 2, where sine is equal to 1. Remember now, cosine starts at 1 and heads down. Sine function starts at 0, 0, 0, and then heads up. We start decreasing at pi over 2. We pass through the x-axis at pi. Down here at 3 pi over 2, we begin to start increasing again, and we go to 2 pi. So from this point to this point, with the green graph, from here to here, I see that I've made one full cycle. I started up, went down, went back up, hit the x-axis again, but I'm still going to be traveling up. I got a period of 2 pi. Now, what happens with this second function, g of x equals 3 of x? What's happening to my period? Well, first let's look at it algebraically, because we remember that to find the period, we got 2 pi over the absolute value of b, which in this case is 3. Well, the absolute value of 3 is 3, and so our period is 2 pi over 3. Well, let's see, 3 pi over 3 would be 1 pi. And let's follow this red for a moment. So I'm going up from the origin. I hit 1. I start coming down. I'm not really at pi over 2 yet. Down here. And we come back up. And so my period here is right here. Well, is right here. So I got a period running in this one. Well, right here is pi. Right at this point, we've come back to pi. So I'm a little bit less than pi. I'm greater than pi over 2. And so that matches that my period in this case would be 2 pi. Now, what's happened to this thing? We've got and I should have addressed, well, I'll address it in the next slide. As I have, if b is greater than 1, which in this case it's 3, it will compress the sinusoidal function horizontally. It will compress it. If b is less than 1, but greater than 0, it will expand the graph horizontally. And we're going to see an example of that coming up right now. All right, so here we got two functions. We've got f of x equals the cosine of x. It's our parent function. We see that in green. My period goes from this point right here to this point right here. Once again, it's 2 pi. And then we've got g of x, which we see graphed in red, which is the cosine of 1/4 x. Now again, algebraically, let's think about what's happening with our period. So to determine that algebraically, I've got 2 pi over the absolute value of b. In this case, that's 1/4. And so this is going to equal 2 pi times 4, dividing by 1/4, same as multiplying times the reciprocal. And my period has now expanded from 2 pi out to 8 pi. And it's so far that I don't even have it on the graph here. You can see we started here in the red. We start heading down, which is characteristic of that cosine function. But by the time we would reach 4 pi, and you can't see it, I'm beginning to start to make a turn and head back up. But my period is going to be 8 pi. All right. Horizontal dilations. If it is greater than 1, it compresses the sinusoidal function horizontally. If it's less than 1, it expands it. All right, I think next up we look at phase shifts. Anyway, no, I guess actually we talk about frequency. All right. Sinusoidal functions. That's kind of hard to say sometimes. Maybe it's not for you.